So diffusion-based partial differential equations, and how do they relate with the hyperbolic conservation equations that we have treated with the discontinuous Galerkin method? So let me kind of reiterate these two sets of equations. We have, for scalar hyperbolic conservation law, we have the time derivative of our scalar plus the divergence of some sort of flux function that depends on our solution field. And that would be 0, say. So this is our hyperbolic conservation law. And what would be a typical example of a diffusion-based problem? Well, that would either be an elliptic problem or a parabolic problem. I'll treat the parabolic one. That would be the heat equation, just to kind of emphasize the similarity with this one here. So the heat equation looks like this. Now, so we do see some similarities here. We have the same time derivative, and then we have this divergence term. And this divergence term kind of made this a conservation law. So also the heat equation is a conservation law. Now, it's not hyperbolic, and the reason for that is precisely this other derivative operator. Right? We said that in this flux function, the f really only depends on the value of phi and not its derivative. But right now we have sort of a flux function, which we actually also call a flux function, but it depends not on phi, but its derivative, right? So you would be able to write this something more along the lines of, and I can even make it a plus by changing the definition. So f of gradient of phi. Yeah, that would be sort of the equivalent statement here. And these f's in all cases are vectors. So that is we could call this a parabolic conservation law. And actually specifically the lower one would be general form of that. And the specific case that we're interested in is then the middle one, right? So we have this diffusion term in there. So clearly we have to be able to treat terms like these, and if we compare that with what we did before, where the trick in the discontinuous Galerkin method was really in the treatment of this guy, but then on the boundary, right? That's why we introduced a numerical flux, a numerical approximation to our flux function f, given that we have a certain discontinuity and that we have an ambiguity in terms of what phi to pick. So we would do something similar now for this diffusion term. But before we do that, I kind of want to move a little bit closer to the expression that we have on the top. So something that looks a little bit more hyperbolic, even though at the base it's still parabolic. And the way that we do this is by an introduction of a new variable, which we call an auxiliary variable, sigma, which we actually define to be this f here, or the gradient of kappa. And we call this a reduced order formulation. Well, this one would be a star. The way that we would do this is we write our second order partial differential equation as a combination of two first order partial differential equations, where I have first my conservation law, and I'm now going to introduce a new variable which I'm calling sigma, and that's going to be equal to 0. And in order to do this, I would have to write the definition of sigma, and sigma is going to be defined as the diffusive flux minus kappa times the gradient of phi. So this is an equivalent partial differential equation. We've introduced a new variable, and by doing so we have something that in a sense looks a little bit more like what we started off with, right? That we have a flux that depends on the value of a certain state at that location rather than its derivative. Now, of course, this is just a matter of notation because the derivative is still hidden in there, but in a more direct sense, we now have a flux function that depends on a state at a location. So that means that we can proceed in a manner that's very similar to what we did before, with the difference that we have to treat two equations. Now, this is actually something that we've also seen before. We talked about mixed methods, mixed formulations, where we had the Stokes equation as our typical example. And that was also an equation that involved two sets of equations. So that's not something that is completely out of scope here. This is something that we've also seen. And the way that we did that, or the way that we treated the Stokes equation, is that we take both of these equations separately, and we multiply both of these by a certain appropriate test function, integrate, and we do integration by parts. Right? So that's what we'll also do right here. As I proceed, I'll actually operate under the assumption that we are in the steady limit. So the case where phi is t, phi of t or phi sub t is equal to 0. And it's absolutely unnecessary, but it's going to simplify my equations a little bit. Yeah? And in a sense, we're actually interested in treating the Laplace operator, and that's precisely what you would get if you would cross out this phi t right over here. Okay, so what happens if we consider that case, and if we proceed as what I just pointed out? So we multiply by a test function, integrate over the domain. But now we have the intent of using discontinuous basis functions later on. And we're going to use discontinuous basis functions for both the field phi and the field sigma. So that means that I am limited to what I'm allowed to do in terms of the integration. And our trick last time for the hyperbolic conservation law is that we're first only going to look at a single element. So I'll do the same thing here. So I multiply by a test function. Well, the first equation is a scalar equation. So I get multiplication by a scalar, let's say w. Then I integrate over the domain. But let me quickly scroll up to see how I've been writing this before. Whether I've been using inner products or... Okay, I've been using actual integration signs. Let me stay consistent. So we're going to integrate over a single element. And that has to be 0 for all choices of w. And we'll look at the relevant spaces later on. Second equation, well, it's going to say that the integral of k of sigma, but this is a vector equation, so I have to have a vector test function. So we're going to dot it by tau. And I'll just move whatever is on the right-hand side to the left-hand side. So you get plus the integral over k of kappa gradient phi dotted with tau. And that's also going to be equal to 0, in this case for all tau. So what was the next step in our derivation of the discontinuous Galerkin method? Well, we did integration by parts, and we did integration by parts on each element separately, because that's going to give us certain boundary terms, and we'll play around with those boundary terms. So in our earlier approach, we had only one equation, so we did integration by parts on this term. But now we have two equations, and we can, if we want, also do integration by parts on this term. Now, this is not necessary, but it will introduce additional boundary values of, in this case, phi, as we'll see in a second. So it's going to give us more flexibility in terms of choosing numerical fluxes, and as a result, we can get more different choices of methods. And after that, we'll have to think about what kind of methods are appropriate and useful. But in order to make ourselves comfortable and have a range of choices, what we're going to do is we're going to do integration by parts on both of these terms. So the first one is a straightforward use of the divergence theorem. We get minus the gradient of w dotted with sigma. And then we get a boundary term. And that's going to be equal to 0 still for all w. And this is before I discretize anything, right? This is the original partial differential equation. So I don't have any issues yet with discontinuities. So the second term, of course, we get something similar. And our integration by parts formula would be, minus k kappa divergence of tau phi plus partial kappa of tau dot n times kappa phi. Partial k, sorry. K is the element, right? And this is going to be true, it's going to be to 0 for all t, tau. Let me make sure I didn't make a mistake. I think that's fine. So we had a strong form here, integration by parts, integration over our element here, integration by parts here. And now we're going to introduce a discontinuous Galerkin approximation space. And now we're going to say we're looking for a solution, an approximation, phi h and sigma h, right? We're trying to approximate now both fields in spaces, well, let's call them wh and sigma h, such that we have that the integral over k, let's scroll up a little bit here. Can I do that? Minus the gradient of w dot sigma h plus partial k sigma h dot nw is equal to 0 for all w, well, in that same space. Well, let me actually get rid of this h yet, and I'll get back to that in a second. And as our second rule, we have integration over the element of sigma h dot tau minus the integral over the element of, we say, divergence tau of kappa phi plus the integration over the element boundary of tau dot n times kappa phi, this is phi h, sorry, and that's equal to 0 for all tau in sigma h. Okay, so now we've introduced a discretization, and our discretization is such that on an element boundary we can have two values, one on each side of the element boundary. So that's where we had this ambiguity for all of these values on the boundary. So that would be this guy and this guy. So that's where we get the flexibility of choosing numerical fluxes. So I will replace this phi. It should be simply kappa phi and sigma dot n, but I'm going to replace that by some numerical treatment of our solution on either side of the element interface. So we have two numerical fluxes. We have sigma h, and just to be clear, in principle, sigma hat is a function of sigma plus, sigma minus, right? The value of sigma on either side. It would also be allowed to be a function of phi on either side, if we want to design a numerical flux like that. And in certain cases, we even write it as a function of the normal gradient of phi on both sides of the interface. So we can put all kinds of stuff in our definition of of sigma hat. And so similarly, phi hat is also going to be a function of, well, phi on the one side of the interface and phi on the other side of the interface. Let me quickly look ahead here. Okay, yeah, and there's even one case where we also choose to include sigma from either side of the interface in our definition for this numerical flux. Yeah, so you can already see that, well, there's a whole bunch of choices to be made here for these numerical fluxes. We could take values on one side, we could take values on the other side, we could take combinations, and now we can even take combinations of different fields, as long as we try to be consistent and conservative. And those are the two properties that we wanted to maintain, given the true nature of the physics. Okay, then there's one last step in the derivation that I'd like to do. Not two even. What I'm going to do is now, after that I've introduced this numerical flux, well, then this is just a function of phi and sigma, and this numerical flux over here is a function of phi, sigma, and maybe even the normal gradient of phi. But it's a fixed function at that point. So if I want, what I can do is I can, after this, I can again do integration by parts on this term right here. And I get a slightly nicer formulation, is why I'm doing that. So you would then say find, well, again, phi h and sigma h in our spaces wh and sigma h, such that, and I'm going to do integration by parts again backwards, really, in my element interior. So then I get a plus, and I get sigma, get the divergence of sigma times w. Then I still have this term right here that remains fixed of sigma hat dot n. And actually, typically we have a numerical flux specifically for the normal direction, right? So you would actually get something like that. Also a normal here on the right. Times w, but now minus a new term, because I did integration by parts, of sigma dot n, sigma h dot n times w. Yeah, and you should recognize now that these are not necessarily the same, because I have some arbitrary choice for sigma hat. So these are not going to cancel, and that's why doing integration by parts back and forth still gives me actually a bunch of terms in the boundary. And for the second one, I'm just going to keep the same expression. Let me just copy that over. Replace this by just a phi hat, and we have both of these. Okay, so the reason why I did this is purely because it looks nicer. There is absolutely no difference with respect to the previous equation. Now, why do I say it looks nicer? We have a certain symmetry here. Yeah, we have divergence of sigma hat h, and we have a divergence of tau here, multiplied by a scalar, multiplied by a scalar. And we have a tau dot n multiplied by a scalar, and here we have a sigma dot n also multiplied by a scalar. Now we'll see later on that symmetry maintains symmetry after we've substituted certain choices for our numerical fluxes. So it's just a nicer formulation. Other than that, there's really no difference. And this term by itself is actually also symmetric, in the sense that if I flip my test and trial functions, you'll see that, well, this term is going to be the same, right? So pretty much everything here is symmetric. Okay, and then as a last step in a derivation, what we want to do is we want to not consider one element, we want to consider all the elements combined. So we're going to sum this up for all elements. And then we had this introduction of our broken domain. So those were the element interiors. We have our gamma as our mesh skeleton. The set of all element interfaces. And then we had our definitions of these jump and these averages. And if we then sum over all these elements, what would you get? Well, you would, let me actually write this out again. Find phi h comma sigma h in wh cross sigma h, such that well, we have an integration over now this broken domain, right? This is sum over all element interiors of that expression, divergence of sigma h times w. And now we have the sum over all of these. And we had a nice identity for that a while back. Maybe I can still find it here. That's an identity that I'm asking you to show or to prove in the homework assignment. That's this one, right? So if I sum things from either side of from either edge, from either side of the element, then they can write that as the average times the jump plus the jump times the average. And that's precisely what we're doing here. Because this is an integration on the element interior side of the interface, so the edge, but only on with the values on one side. And this is the same thing, right? We're integrating W and sigma, they're all from the element interior. So we can write these quite nicely as plus integrations over our mesh skeleton of the average of sigma hat times the jump of W. This will be a dot product. Plus the jump of sigma hat times the average of W. And the same thing for this other term that we had, where we have now the average of sigma h times the jump of W plus, was that a plus? Probably a minus, right? No, excuse me. Ah, okay. Plus the jump of sigma h times the average of W. And as our second, and this was 0 for all W in WH. And the second expression works out quite the same. So we have an integration of a broken domain of our sigma h dotted with tau, plus an integration over our broken domain of divergence of tau times kappa phi, plus an integration of our mesh skeleton of the average of our kappa phi, our numerical flux, times the jump of tau, plus the average, times the jump of our numerical flux, times the average of our test function tau, and now this will be a dot product. Okay, and this is also going to be equal to 0 for all tau in sigma h. Okay, so this is the formulation that I'll use. It seems quite lengthy, but I hope that all terms are clear. It actually simplifies a little bit if our fluxes are conservative. We talked about what that meant, and practically what that meant was that our fluxes have a 0 jump. So that means that, well, this guy is 0 if it's conservative. And this guy is 0 if it's conservative. And then if they're also consistent, then we'll actually find that a couple of these terms in here would also collect with or cancel against some terms in here. But we'll see that in the next video. What I wanted to do here was provide this general formulation for the diffusion problem with the discontinuous Galerkin method. And in the next video, I'll show you that there's a whole bunch of choices again for the numerical fluxes, both for the sigma and for phi. And I don't think I'll go into too much detail for all of the methods, but I'll pick one method specifically and derive the full expression after we substitute our numerical flux. And then you can see that they can actually end up being quite nice and quite simple. Okay, so that was all for this video. Thank you for your attention.